In this guide, why the OpenID provider issues two separate tokens and what each one is actually for. The full claim anatomy of the ID token, including auth_time nonce ACR AMR, and which profile claims only appear when specific scopes are granted. The access token profile defined by RFC 9068, why the type header at+jwt exists and how resource servers should use it. And how both tokens change across every stage of the session lifecycle. Initial login, silent refresh, step-up MFA, and logout. Plus practical guidance on where to store each token and when to call the userinfo endpoint. Identity Expert, powering you to be an expert in identity. Picture this: a developer ships a single-page app that sends the ID token as a bearer header to the backend API. It works in dev because the API never validates the auth claim. Months later, the team enables audience validation in production, and every authenticated request starts returning 401. The fix takes 5 minutes. Swap the ID token for the access token. But the outage took 4 hours to diagnose because both tokens decoded as valid JWTs. Every OIDC login issues two tokens. A surprising number of developers send the ID token to APIs or use the access token to establish user identity. One fails the audience check. The other silently trusts a token that may carry no user claims at all. They are not interchangeable. In the next 10 minutes, you will understand exactly why. Think of it as a passport versus a credit card. The ID token is your passport. The government, your OpenID provider, issues it. The border agent, your app, checks it once at entry, extracts what it needs, and hands it back. You do not give your passport to shop merchants. It proves who you are. You don't reuse it for purchases. Notice that the passport has a photo and a nationality. Those are like the profile claims: name, email, picture that only appear in the ID token when the right scopes are requested. Without the profile scope, you get a passport with no photo. The access token is your credit card. The bank, the authorization server, issues it. Every merchant, every API swipes it. It has a spending limit, that is your scope. An expiry date, that is exp. A fraud number, that is JTI. When it expires, you get a new one silently via refresh. Your passport never touches the payment terminal. There are two developer mistakes that come up again and again. Mistake 1, sending the ID token to an API. This fails the auth check immediately. The ID token's auth claim is set to the client_id, not the API's URI. Even if the API accepts it, it is now trusting a token minted for a completely different party. That is the confused deputy problem. In real-world integrations, a microservice that accepts any valid JWT without checking auth will happily process an ID token. Nobody notices until an attacker crafts a malicious client, obtains an ID token for the same user, and replays it against the API. The signature checks out. But the audience was never this API. Mistake 2, using the access token to establish user identity. Access tokens may be opaque strings with no user claims at all. Even when they are JWTs following RFC 9068, the subclaim alone is not safely usable without also verifying IS. A subvalue is only unique within a single issuer. Two identity providers can issue tokens with the same sub for completely different users. The correct approach is to call the /userinfo endpoint with your access token. The userinfo response is authoritative. It reflects the current state of the user's profile, not a snapshot from login time. If the user changed their email or revoked consent, userinfo returns the updated values. Here is the full flow from login to API call. Step 1. The user authenticates at the OpenID provider using authorization code plus PKCE. Step 2. The OP issues an ID token, an access token, and a refresh token together at the token endpoint. The ID token is assigned JWT with type JWT. The access token carries type at+jwt, or may be an opaque reference depending on the provider. Step 3. Your app reads the ID token, extracts sub name, email, auth_time, and ACR, sets the local session, and then discards the ID token. It is not stored long-term. The ID token's job is done once the session is established. Step 4. Token storage matters. The access token should live in memory, a JavaScript variable, or in memory store, never in local storage. Local storage is accessible to any script on the page, including XSS payloads. If you need the token to survive a page reload, use an HTTP-only secure cookie with same-site equals strict. For server-side apps, store it encrypted in your session store. Step 5. Every API call sends authorization bearer followed by the access token. The resource server validates the signature against the OP's JWKS, checks IS, checks auth, matches its own identifier, checks exp, and if the token carries a JTI, checks it against a replay cache. Step 6. When the token expires, a silent refresh produces a new access token only, no new ID token. Auth_time is unchanged. Step 7. If a step-up is needed, a new auth request with ACR_values triggers MFA, producing a new ID token with an updated auth_time, ACR and AMR, plus a new access token with the elevated ACR. Step 8. At logout, clear the local session, call the op/logout endpoint, and revoke the refresh token explicitly. Here are both tokens side by side. On the left, the ID token. The header carries ALG RS256, type JWT, plain JWT, not at+jwt, and a kid pointing to the signing key in the OP's JWKS. The payload carries is, sub, and crucially odd set to the client_id, not the API. It carries IAT and exp. Then auth_time, the epoch second when the user last actively authenticated. A silent refresh preserves the original value, so your app can detect stale authentication. Next, nonce, a one-time value your client generated at the start of the flow. The ID token echoes it back. Your client must verify the match or reject the token. Then ACR, the authentication context class reference, a string like earn:_example::MFA indicating the assurance level. And AMR, authentication methods references, an array like password plus auth listing the factors the user actually used. Finally, scope-gated profile claims like name, email, and picture only appear when the client requested the profile and email scopes. On the right, the access token. The header carries type at+jwt per RFC 9068. That type value lets a resource server distinguish an access token from an ID token at the JOSE layer before parsing the payload. RFC 9068 requires resource servers to reject any token whose type is not at+jwt. The payload carries is, sub, and odd set to the API URI, not the client, plus exp, IAT, JTI for replay detection, client_id, scope, and ACR. The critical structural difference is the odd flip. ID token odd equals client_id, access token odd equals API URI. That single claim determines which party is the intended audience, and both sides must check it. 6. Threat and mitigation pairs. First, sending the ID token to an API mitigation, the API checks odd. The ID token's odd equals client_id, so the check always fails for an API audience. But this only works if the API actually validates odd. Many microservices skip this check. Every resource server must validate odd, no exceptions. Second, using the access token for identity when it is an opaque token. Mitigation, call the /userinfo endpoint with the access token to get fresh, verified identity claims from the OP. Third, ID token replay due to missing or unchecked nonce. Mitigation, generate a cryptographically random nonce per authorization request, store it in session state, and verify the nonce claim in the ID token matches exactly. Fourth, stale ACR, a resource server accepts a basic auth token for a high-security operation. Mitigation, enforce the required ACR level. If the token is too weak, RFC 9470 lets the resource server return a 401 challenge specifying the required ACR_values and max_age. Fifth, access token theft from memory or a log file. Mitigation, DPOP per RFC 9449 or MTLS sender constraining, short exp. JTI replay cache, and never log tokens, log a truncated hash instead. Sixth, tokens stored in local storage vulnerable to XSS mitigation, store access tokens in memory only or in HTTP only, secure cookies with a strict content security policy. For refresh tokens, use HTTP only cookies with same site equals strict and rotate on every use. The ID token and access token split is becoming more rigidly enforced across the ecosystem. OAuth 2.1 normalizes the separation. PKCE is required for all flows, the implicit grant is removed entirely, and access token audience binding is a recommended baseline. RFC 9068, the at+jwt type header, is now the standard access token profile. Auth 0, Okta, Microsoft Entra, and Keycloak all emit it by default. If your infrastructure still issues plain JWT access tokens without the at+jwt type, update your configuration. Compliant resource servers will reject them. DPOP per RFC 9449 is seeing growing adoption to sender-constrained access tokens, making a stolen bearer token useless without the matching private key. FAPI 2 mandates PAR and JAR for authorization requests, requires strict odd validation on both token types, and requires sender-constrained access tokens, either DPOP or MTLS, eliminating plain bearer tokens for high-security profiles. And the userinfo endpoint is gaining importance as the canonical source of user identity, replacing the pattern of caching stale ID token claims in long-lived sessions. The primary references for this guide: OpenID Connect Core 1 Sections 2, 3137, 5.310 and 12, covers the ID token structure, token endpoint response, the userinfo endpoint, and claim types. RFC 9068 defines the at+jwt access token profile and its validation rules. RFC 9470 specifies step-up authentication challenges. RFC 9449 covers DPoP proof of possession for sender-constraining access tokens. RFC 9700, the OAuth 2 security best current practice, consolidates hardening recommendations for both token types including token storage guidance. And the FAPI 2 security profile specifies the strictest production requirements for audience validation and sender constraining. If this guide helped you understand where the ID token ends and the access token begins, hit subscribe. Every Identity Expert video covers one IAM concept from first principles. No filler, no hand-waving. If you have seen the token confusion bug in production, drop a comment. We would love to hear the war story. And if there is a topic you want us to cover next, leave it below.